Well, hello again. Today we're going to talk about solid fuel combustion. So we've been talking about getting the heat into a kiln. Previously, we talked a lot about liquid and gaseous fuels. Today we're going to talk about solid fuel combustion. Now, I really didn't originally plan to have a lecture on solid fuel combustion, but there's some safety aspects of solid fuel combustion that you need to know about. Even if you don't use solid fuels, you have combustible solids around the plant, and you really need to know some of the information that's going to be presented today. So if you don't use these solid fuels, that's okay. Hang with me and let's try to talk about the safety topics. Now, last time, of course, we were talking about liquid and gaseous fuel, and we talked about burner control in kilns being by linking the airflow to the gas flow. That's so that we can maintain on ratio combustion in the burners as they're modulated from low to high fire or back down to low fire, wherever they are set. So the linked valve or linkage with ratio regulators has been around for quite a while now. In more recent technology, high velocity burners were developed. These burners allow for the heat of combustion to create pressures that propel the hot combustion gases and some of the fuel elements and flame out across the kiln enclosure. We get a lot better heat distribution in kilns with high velocity burners, and consequently we encourage convective heat transfer and we reduce energy consumption with high velocity burners. These burners use pulse firing technology, or as it's called by North American in their trademark, step fire. And so therefore, this has been a major advance in firing technology and conservation of fuels. We talked a lot about burner placement strategies, and the basic idea is that heat rises. So we can place burners low in the kiln, in a tunnel kiln, in a periodic kiln. We can place them such that they create a swirl and make the combustion gases move through the product setting that's in the kiln. Again, we're trying to encourage convective heat transfer. We also know that some kilns are top fired. So generally the flame or the combustion takes place in firing lanes or open spaces where the product is not set, so that we avoid flame impingement. Index fire is one of the ways that we accomplish that with in tunnel kilns, with the burners being cut off as the product is being moved under the burners, with the firing resumed once the kill car is in position, so that there's no flame impingement. We talked a lot about safety last time, and my particular focus in the lecture is about purging the kilns of combustibles so that you cannot have an ignition and a kiln explosion. There are many aspects of fuel safety that we didn't cover, but that's one that I really wanted to emphasize in the lecture. So today we're going to talk about solid fuels, and solid fuels were the original fuels used in ceramic kilns. Wood and later on coal when it was available, used in lump form or large pieces of wood. In today's world, we use pulverized fuels, fuels that have been crushed or shredded so that we get different handling systems. We don't use stoker systems or burners where lump coal is injected into the side of a round kiln, for example. We are crushing the material and pneumatically injecting it into the kiln, as you will see today. Coal firing has declined in many parts of the world due to carbon dioxide emissions and its effect on global warming. It's been replaced in some cases by waste fuels, which are considered environmentally friendly in that we eliminate a waste product and don't put it into the environment as a solid waste. Well, it's always important to consider safety, and we will again with solid fuels. We'll talk about fire and explosion potential of solid fuels. We'll talk about solid fuels from a standpoint of environmental impact and on worker safety, worker inhalation. So let's get started and talk about fuels a little bit. Here's some values for calorific value of solid fuels based on a unit of measure that we are accustomed to using. In the inch-pound system, pulverized coal, 10,000 BTUs per pound. It may vary up and down depending on the type of coal that we're using. So these are our general values. Fuel oil number 6, 150,000 BTUs per gallon. Wow. Liquid fuels are packed with energy, and that's the reason that they are used so much in transportation. Natural gas, the rule of thumb is about 1,000 BTUs per cubic foot. Sawdust is less than that of pulverized coal, about 8,500 BTUs per pound. And just for comparison, I listed gasoline and diesel fuel. Now, of course, these fuels have vastly different densities in the unit system that we want. With natural gas, I've always heard that air releases in combustion about 100 BTUs per cubic foot of air. Well, see, we use 10 parts of air per part of natural gas by volume. So 10 parts or 10% of 1,000 is 100 BTUs released per cubic foot of air, where 1,000 BTUs per cubic foot of gas is released. That's just another way of looking at the combustion process. Now, when I taught this course at the university, and when I still teach it, I talk about air emissions related to pounds of pollution per million BTUs released. And so I base this on something called the AP42 or Air Pollution-42 volume published by the United States Environmental Protection Agency. So I have some numbers here that sometimes they're surprising, comparing natural gas, coal, fuel oil, sawdust, and I put in some internal combustion engines here just for fun. But NOx, nitrogen oxides emissions, natural gas is up here about 0.235 pounds per million BTUs, but look at coal, much lower. That's one of the advantages of coal firing and ceramic kilns, that there are very little NOx emissions, and that could be important in areas where there's a lot of vehicular traffic. We call those attainment areas in the United States. Well, sawdust, another solid fuel, is much less than natural gas. So that was a little bit surprising. But of course, sulfur is the big problem with coal, along with particulate matter. With fuel oils, we can get soots being formed. Here are some values for carbon monoxide and total suspended particulate matter. Filterable particulate is a fraction of that total suspended particulate matter, and you can see that natural gas has 0.0019 pounds per million BTUs, but coal is much larger in filterable particulate matter, and sawdust is much larger than that of natural gas. So in general, particulate matter release during firing of solid fuels, forming ashes, is something that's very important, not only from an environmental standpoint, but also from a worker safety standpoint. There are some metals given here. These get to be some pretty small numbers. And of course, there is concern of mercury emissions with firing of coal. Now, here are some properties of the solid fuels that we normally see around ceramic plants. It's compared to, of course, a liquid fuel oil. But nevertheless, I want to say that these are general properties. It depends on the source of the material, but here are some more values that you can see in soft coal being about the same calorific value as hard coal, anthracite, lignite, a fairly impure carbon source, is a little bit less. So we have volatiles in these fuels. The solid fuels, particularly coal, you can see a proximate analysis sometimes that is, in my opinion, an approximation of the fixed carbon, the volatile matter, and other species like that. And then you can have an ultimate analysis, which is like a chemical analysis. Now, here are some ignition temperatures. These are ballpark figures. You can see that sawdust ignites about 600, just like charcoal, and soft coal a little bit higher than that. But I'm going to show you a slide in just a minute that shows much lower values for pulverized material. So that's what we're using today, pulverized or shredded solid fuels. And the most important thing here is that the ignition temperature of shredded fuels really depends on the particle size and the moisture content. Okay, drier and finer solid fuel powders ignite at much lower temperatures. So you really have trouble if you try to Google ignition temperature for sawdust or soft coal. You're going to get some information that says, well, it can depend. Or maybe we just don't publish a value, and it depends on the particle size and the moisture content. Now, in my laboratory, I've measured ignition by looking at differential scanning calorimetry. I've shown you this slide once before. The green line is a brick material or brick clay that's being fired. And here in the realm of 500 to 600 degrees C, it has an endothermic reaction due to dehydroxylation, removal of the hydroxyls, or the chemically combined water, as we call it, from the crystals. If we start adding coal, we're going to see a little exotherm at low temperatures, generally between about 300 and 500 degrees. That's when the volatile matter is coming out of the coal and ignites in the laboratory instrument I was using. And then later on, you'll get another exotherm here, and the endotherm's gone. So the ignition of the coal, or the carbonaceous matter mixed with the clay in this case, got rid of the endotherm, and actually we have some net heat released. And if we go up to a higher percentage of coal, I think this was 3% in this case, the blue line shows you the low temperature volatile ignition as the volatile matter comes out of the coal powder and ignites. Exothermic reaction reacts with air or oxygen in the air. And then we get the higher temperature exotherm here at 500 to 600. So what is the ignition temperature of this coal that's pulverized? 300 degrees and higher. It's not, as we saw before, 700 to 1100. So it really depends a great deal on the state of pulverization of the material. Much lower temperatures for finer materials and dry materials, as they were in this particular instance. Now, you can find some utilities out there that talk about solid fuel combustion. I used one from an engineer named Barnes that I found on the internet. I don't know if it's still available, but it was not a Windows program. It was an old Excel program. And so you had to pick the fuel that you wanted. And in this particular case, I took anthracite coal, hard coal. The gross heating value or high heating value for the fuel was 12,680 BTUs per pound. It's a little confusing because with a solid fuel, it's going to be BTUs per the weight that we normally use, pounds, whereas with gas, it would be cubic feet, and obviously liquid fuels would be gallons. So he lists all this up here. And you had to give a temperature, so I used 2,000 degrees Fahrenheit as a furnace temperature. Excess air used 30%, not too uncommon for coal, could be much higher than that. And then it went through its calculation. And so there are some emissions here, but the available heat from the coal was 4,604 BTUs per pound, even though it had a high and low heating value of above 12,000. We're using a lot of excess air and we're heating up a lot of products of combustion. So in essence, the program computed a 36.31% efficiency of combustion. So you can obtain this program, perhaps. It's one that I've used for a long time. Another solid fuel that's been used in more recent years is petroleum coke. You can see some data about petroleum coke. It's the residue from refining of oils, and it is crushed and used in combustion. It's considered a recycled fuel, and therefore it's preferred in some areas of the world. I took some of a product called United Petroleum Coke and heated it up. This is a thermogravimetric analysis, weight loss versus temperature. And you can see that it starts losing weight up above 400 degrees, and combustion is pretty well complete above about 600 degrees. So you lost all the weight as the carbon burned out, and you're left with ash above about 600 degrees. So there are various ways to determine ignition points of solid fuels as well as liquid fuels. This is the way that I have done it in my laboratory because it's really convenient. Just use the thermal analysis equipment that I have available. Okay, let's talk about firing solid fuels. And we're only talking about the modern world in industrialized countries. We're not talking about firing lump coal or cords of wood or something like that, saw cut timber. We're talking about crushing and shredding the fuel, drying if necessary, being careful about how much moisture we remove, pneumatic transport of the fuel up to some proportioning device. That proportioning device is going to insert it into air segments that are blown into the roof of the kiln. So pneumatic transport is typically what's used. We're transported to the top of the kiln, and then the solid fuel particles drop down into the kiln enclosure. They fall by gravity and ignite. You can see them igniting. Particularly coal is interesting because you can see glowing particles dropping down into the kiln as the ignition of the carbonaceous matter takes place on the surface of the particles. Now, I had a friend in the business, Hans Lingel. The Lingel company in Germany makes kilns and other devices for the ceramic industry. Mr. Lingel was very kind to me during my career, and so I inserted a picture of him, and here's one of his patents. And since I didn't have pictures of solid fuel systems, I used patent drawings. So the coals from a crusher is taken through a rotary dryer in this particular instance, okay? and it's dried to a specified moisture content, dropped into a hopper from the rotary dryer discharge. A screw auger elevates the kill into, the solid fuel into a bin. And then that bin blows the pulverized fuel and dried fuel up into a distribution device, which you're going to see, which distributes it through burners. So this shows it dropping downward into a kiln. Here's the distribution device shown in a little more detail. There's where the material is blown into a collector device. It drops into a rotating plate, and the plate has a slot in it. So it drops individual segments of coal down into a place where it's blown over into the roof of the kiln. So the distribution device sits on top of the kiln. It's falling by gravity, and it's blown into the kiln. And so this depicts a burner and refractory lining in the crown of the kiln. Devices like this are used both with coal and with wood dust, wood flour, sawdust, if you want to call it that, in the United States. So there's a little more detail of the distribution device. Here's the accumulated coal. The plate is here. That's rotating, dropping the material down where the air supply here propels it into the tube going to the burner. So on top of the kiln, it looks like this, with one distribution device, in this case shown supplying about 12 burners. And so these look like little tubes on top of the kiln where the solid fuel is blown down into an opening in the crown of the kiln where it falls down and is ignited. A lot of people say this looks like a spider, so they call it a spider on top of the kiln, just common vernacular. Now, of course, lighting one of these kilns is pretty exciting. You have to get it, the kiln above the auto ignition temperature of the solid fuel in order for it to burn in the kiln. And so there are various techniques to do this with gas burners. I've even known of people loading up kiln cars with wood and running them through the kiln on fire while they start injecting the coal until they get up to the temperature at which the coal will automatically stay ignited. When the kiln's hot, then the product is run through the kiln. Now, it's very important for me to talk about dust explosion potential. Dust explosions occur with any combustible powder. So this happens with foods. Dust explosions in the United States happen sometimes with grain elevators, where grain is a solid organic material and it's being conveyed pneumatically into the grain elevator, as it's called, the bin or silo where it's stored. And so you have to consider that with any time you're handling solid fuels. I'm going to tell you a little story about what happened in the initial stages of sawdust firing in the United States, where it wasn't considered. So I'm going to offer a screening test. And this is simply a screening test. It's not a definitive and conclusive method to tell you whether a dust explosion can occur, but it's a quick test that you can use. Most important thing to know is that dust explosion potential increases, dust ignition potential increases as the moisture content of the powder decreases. The drier the powder, the more apt you are to have ignition. And of course, ignition of a powder cloud is the same as a bomb. It's essentially like a gas flame ignition. and it can be catastrophic. So one time I operated a plant that was processing dried carbon, and I wanted to find out if there was any dust explosion potential, because I wanted to protect the workers. And so I hired a professor who came over, and he was a chemical engineering professor, smart individual. He said, well, give me a handheld torch and give me some of your powder. And so he ignited the torch. There's the torch flame going through here. And he took a spoon or eating implement and just sifted the powder down into the flame. So in this particular case, this is powdered sugar. Powdered sugar will ignite with a plume of fire and continue burning as it drops down to the desktop. Okay. Sawdust will also have a little bit of ignition right here, but not nearly this much, and coal dust will as well. If you take a ceramic powder like clay or aluminum and drop it through there, nothing will happen. Why? It's not ignitable powder. The reason I use sugar in this example is a few years ago in the United States, near the city of Savannah, there was a dust explosion in a powdered sugar facility, a facility that ground granulated sugar and produced powder and packaged powdered sugar. And they had been operating for many years, never had a problem. Then one day they had a dust explosion, and unfortunately, I believe it killed some people. That's the nature of dust explosions. The atmospheric moisture, the humidity, meaning, and the moisture content in the sugar, the source of ignition, all must be there. And if all those items are exactly right, you're going to have an ignition and maybe an explosion. So this is a screening test. It's offered only for your consideration as a screening test, not as a definitive test. If you expect a dust explosion, then I recommend that you certainly get your safety personnel involved in evaluating this potential using more advanced analytical tests. One of these is called a bomb calorimeter, which you can inject you can have the material in the calorimeter, and you can test it at different moisture contents with different atmospheres. Now I'm going to tell you a little story, a true story about the first time that wood flour was injected into a clay brick plant in the United States. The company switched over from natural gas combustion to shredded wood combustion. So an engineer that I know and respect set up the system, very similar to what you've seen. Shredded wood was conveyed pneumatically up to the top of a kiln and then conveyed into burner ports or openings in the kiln. There was a lot of research and development to prove this method. And so once the method was adopted, the company notified their insurance carrier that, hey, we've switched fuels. And the insurance company said, well, we're going to send out a safety expert and investigate and make sure that you're meeting all of our criteria for insurance. So the insurance investigator was there with the engineer I know, and the insurance investigator looked at the engineer and said, what's the moisture content of the sawdust? Well, the reply was, it's bone dry, 0% moisture content. The insurance investigator started running. I mean, he ran as fast as he could away from the plant, directly away from the plant. He left his car there, he just ran. And so my friend went after him, finally caught up with him, several hundred meters, several hundred yards away from the plant, and said, what's wrong? He said, don't you know about dust explosions? That's when my friend learned that he shouldn't dry the sawdust to bone dry, that he needed to dry it to a few percent moisture content. Even though that cut down on the combustion efficiency, it prevented the dust explosion potential. So there's a true story about use of solid fuels in ceramic plants. Now we also have to talk about the effects of solid fuels on refractories. This is a particular problem with wood ash, since it contains potassium, and potassium can attack the refractories. So I have seen this reaction in refractories used in refineries, chemical reaction. I've seen it in the brick industry. So we're going to talk about it just a little bit. First of all, let me show you something about the accumulation of wood ash residue as a solid deposit on the sides of a kiln. So you can see where the wood ash dropped down in the kiln and was slowly carried with the draft in the kiln. Of course, it's depending on the air coming down the tunnel, moving from your right to left in this case, because you can see the impact of the combustion right here. So we see a black slag, if you will, or coating on the refractory. Of course, the products of combustion of the wood ash, the ash gets on the product as well. But so one of the problems is this buildup of slag on the product. And of course, the wood ash would negate any possibility of sending a glazed product through this kiln because the ash would really destroy the visual effect of the glaze. But the other thing has to do with the expansion reaction. And so here's our old friend, the potassium aluminosilica phase diagram. And so what happens is the potassium as vapor penetrates the refractory and forms a new compound, and it's called kaliophyllite. Now, that's a whopping big expansion reaction. Within the refractory, it causes a permanent expansion. And here's an example of the first time this was noted in a wall in a wood-fired clay brick plant in the United States. So you can see the expansion was in the outer zone of the bricks that are stacked up here. And that caused the wall to bow outward from bottom to top of the kiln, where there was some expansion allowance. And in this particular case, my memory is that the expansion was so much that at one point they got where they couldn't push the kiln cars because they were locked into position by this bowing out or expansion of the wall. So I have also investigated coal effects on refractories. They're not nearly as severe as the potassium in the wood ash and petroleum coke effect on refractories. And I did this in some detail with petroleum coke and could find no adverse effect in the short term. Now, perhaps one of the most important things to talk about is environmental safety and personnel safety. And we'll talk about both of those, and both of those have to do with particulate matter emissions. Now, I suppose you're aware that if particles are less than 10 microns in size, they can make it through your throat or nose down into your lungs. In general, about 10 microns is a cutoff that scientists use to say now particles are small enough that they can make it into the lungs. So the lungs have to deal with it, and they deal with it in a couple of different ways. That's the purpose of today's talk. But we'll start with the environment. And here are some emission factors in brick manufacturing operations published by the United States Environmental Protection Agency in their volume AP42 that I've already mentioned. And these emission factors are in pounds of pollutant per ton of bricks that are made. Brick production is in units and can be easily converted into tons. So the environmental folks wanted to express these in terms of pounds of pollutant per ton of bricks made. Now, this is a little hard for me to read, so I did take that section out so that you could see it. And so here's total particulate matter in pounds per ton. Natural gas, 0.96 pounds per ton. Now that's out of the kiln. That doesn't mean it came from the fuel combustion, because natural gas is considered a clean fuel. It also means that dust was being conveyed down the tunnel and exited with the gases that exit the smokestack in the brick kiln. So it's not a fair comparison here, but you can see that coal emissions are about double in terms of particulate matter. So definitely firing a solid fuel affected this. Sawdust emissions were not double, and that's in part because a lot of the sawdust residue comes out with the bricks on the kill car. Okay, and the cars have to be cleaned up and vacuumed after that. Of course, that gives the potential for some personnel safety with ash being on bricks that have to be handled. Now, PM10 means particulate matter less than 10 microns in diameter. So you can see that a large portion of these total particulate matters are finer particulates, PM10, that can be in a respirable size range. And turns out the smallest size the United States Environmental Protection Agency could measure at that time in a plant measurement was 2.5 microns. So they further characterized this as 2.5 microns, which they call fine particulates. Well, I don't know about their terminology, but you can look and see that a lot of these particulates in coal and brick firing are pretty fine particulates, and they present a chart here to show that. You can see that sawdust firing particularly gives you a lot of fine particulates, but interestingly enough, they're not emitted out of the smokestack. They go out with a load when the kiln is exited and are dealt with somehow by the brick company at that point. But coal firing and sawdust firing present a lot of fine particulates. Sometimes these particulates are uncombusted fuel particles. Sometimes they're clay particles or components of the ceramic, and sometimes they're fly ash. Fly ash is a particle that can be glassy in nature. And in the United States, we actually have standards for fly ash, as I assume they would in the rest of the world, because fly ash is used in various products, particularly concrete, for example, because it is a fine particle and it has some cementitious qualities. I'm not going to talk about those standards, but I will talk about some of my measurements of one particular fly ash that's been a few years ago. In one of my classes, we did an X-ray fluorescence analysis on the fly ash, and you can see that we found alumina and silica, a little bit of alkali here, and some basic oxide constituents, so a lot of iron. So nevertheless, you would guess at high temperatures that might have glass forming potential, and indeed it does. You also found minor constituents by X-ray fluorescence. In this particular example, mercury was not identified below the detection limit for mercury. And by this particular method, mercury is reported as a concern in coal-fired power plants, large volume operations. So here's a picture. One of my groups of students took a flash, and I think it's a pretty good picture because it shows the spherical particles. So it means that they were liquid when they melted, and they solidified by surface tension into rounded particles. The scale factor here on the bottom right-hand side of the scanning electron microscope picture is the size, up to 10 microns in that length. So you can see some of these particles are close to 10 microns, but a lot of them are very much smaller than 10 microns. So in this particular instance, of course, fly ash can be emitted to the environment because fabric filters aren't very good at capturing particles this small. Now, I am a ceramic engineer, not a medical person, and certainly not an epidemiologist, but I have studied a lot about particles being less than 10 microns diameter and how they affect human health. I know that these particles are drawn into the lungs, and they're drawn into the air sacs in the lungs. At that point, your human body tries to dissolve them. Okay, it tries to let you cough them out. That's not always very easy because these are kind of stuck in little air sacs in the lungs, and then it tries to dissolve them. The problem is that there are certain forms of material that are hard to dissolve. Crystalline silica, quartz, is one of those, and coal dust is another one of those. So we've noticed disease in workers from glass sand plants called silicosis when hard to dissolve particles that are very fine get inhaled by human beings over a lifetime. Okay, so there are environmental exposure regulations by your regulatory agencies, but I have not reviewed the science on all these, but nevertheless, over a lifetime of exposure, human beings tend to lose lung function. And it's because a lot of these particles get lodged in the lung and their lungs become less efficient at working. So silicosis is one of those. Black lung is another. Asbestos inhalation is quite another matter. These particles don't like to dissolve, and they can interact with the lining of the lung and cause a disease called mesothelioma. Now, here's the opinion. There was a study from the British pottery workers, people that are knowledgeable about epidemiology, the science of human health and disease, know about the British pottery workers study, and that's one of the first places that silicosis was identified as a problem in some of the ceramic industries. Well, it turned out in the British pottery worker study, most of these people smoked cigarettes. They used tobacco. And so the conclusion by a lot of regulatory agencies was that ceramic workers tend to get disease like silicosis. Perhaps, I'm going to suggest a more accurate conclusion might be that people that smoke cigarettes and are exposed to silicosis are more prone to disease. I know that smoke molecules, products of combustion of tobacco, are complex molecules. When they go in the lungs, they're present in all kinds of forms, polymeric fragments, molecular fragments. These can condense on dust particles that were entrained in dust in a ceramic plant. And so these are free radicals, if you want to call them that, are drawn into the lung sacs and they're held there. Okay, it's not just deposit of gunk in your lungs, it's deposit of particles that have dangerous, potentially dangerous molecules on their surface. That, in my opinion, is one of the reasons for respiratory disease connected to smoking. But our regulations don't recognize smoking in the United States, and you can speculate why. I think it's pretty easy speculation, but I'm not going to say it. So human beings really need to be protected from fine particulate matter. I worked in research, but associated with one plant that was processing crystalline silica powders. And a lot of workers in the plant wouldn't wear a dust mask, even though it was very dusty in the plant. And I couldn't figure out why. So one day I asked one of the guys why he wasn't wearing a dust mask. And he said, well, I can't chew tobacco and wear a dust mask at the same time because I have to relieve some of the tobacco juice from my mouth occasionally. And I said, fine, well, the tobacco is probably going to get you before the dust does. So both the dust and the tobacco were not good for his particular health. There's some more practical evidence. Back when I became a professor, I became friends with some folk pottery producers up in western North Carolina. That was pretty close to where I was in the United States. I became friends and liked to go talk to them and talk to them about their methods. And I realized that in the early 1900s, continuing on to the middle part of the 1900s, the 20th century, they used wood-fired kilns. Now they had fireboxes where big pieces of wood or lumber, solid logs were charged into the furnace to create the heat, and the heat from that fire went down a tunnel in an intermittent kiln and was drawn out by a chimney effect of a smokestack. So the problem was that after the pottery had been fired, the ware had been fired, they had to crawl into these kilns in order to pull out the stuff they'd fired, because they were pretty long, longer than typically 2 or 3 meters. So longer than a human being's body. So they had to crawl in, and so they breathed the wood ash that was along and trained in the ware. And many of these people developed lung disease. We now call it COPD, but that meant that their lung function was very low, and a lot of them unfortunately also died from the combination of the wood ash and smoking. Okay, well, today we've talked about solid fuels. We've talked a lot about using them in today's world in the pulverizing form. We've talked about how to get them into the kiln so that they can fall down by gravity and burn in the kiln. So pneumatic placement and transport is required. That brings around the idea of the potential for dust explosions. And so I've described dust explosions with any ignitable powder, solid powder, as something you need to be concerned about and follow your company's safety protocols and make sure that they've thoroughly considered dust explosions. We talked about solid fuel residues accumulating on the kiln surfaces and affecting the refractory life, as well as potentially the product quality. We've talked about solid fuel combustion leading to particulate matter emissions. And then we talked a lot about safety, and particularly personnel safety. I had another instance as a professor where I helped a producer of clay roofing tile on the west coast of Africa. That was a very small plant where everything was handmade, and the intermittent kiln was hand set with roofing tile, and it was fired with wood. And that meant that after it was cooled off, the people had to go in and pull the roofing tile out and sell the good product. Now, the manager of that plant was a college professor, believe it or not, but he was a politician, and the wrong political power was in control of his government. So he didn't have a job at the university. He was kicked out. So he made clay roofing tiles. And so I helped him a little bit with some of the problems he had, but then I started talking to him about protecting his workers. And he offered no respiratory protection, no dust masks, nothing else. And I had to talk to him a little bit about the North Carolina pottery workers and what happened to them. And of course, most workers, particularly men, look at the fact that, well, smoky is not going to hurt me, dust is not going to hurt me. And well, it doesn't, short term, but it certainly can over a longer term. And so I told him that story, and I hope that he used that information to modify some of his practices in his ceramic plant in Africa. So that's the reason that I presented this lecture, is I have some experience that in parts of the world, this course may be taken where solid fuels are used. And so I wanted to have my say about use of solid fuels in a pulverized form, dust explosions, environmental and personnel safety. Okay, well, we've talked about getting the heat to the kiln. Okay, we've talked about containing the heat in burners. We've talked about injecting the fuel into the burners and controlling that combustion. It's a little different with solid fuels and liquid and gaseous fuels, in that with solid fuels, we had to depend on the air in the kiln itself to cause the burning of the fuel, the oxidation of the fuel, whereas in liquid and gas fuels, we injected air into the burner system. We had different safety concerns with those systems. Explosions were the main concern and safety, but nevertheless, with solid fuels, we had inhalation of particulate matter that's a product of combustion as a safety concern. Okay, so next we're going to consider the kiln itself, and the kiln is a refractory lined structure. So the refractory is there to contain the heat and create insulation so that you have the least possible heat loss through the walls of the furnace, the kiln. We're going to talk about different types of refractories in the more modern kilns that we use today. We're going to talk about mechanisms of heat storage and heat transfer in these kiln walls, which makes us think about theoretical heat transfer equations. Don't get worried about it, because we're going to use some of the apps in the heat transfer calculations. So you will need to have e-solutions and the thermal conductivity calculator from Morgan if you can get that to work. Next time we'll talk about those. And after that, we're going to do, I planned 4 classes on kiln simulation and optimization. It's how much heat is required for this process. The heat requirement comes from the material that you are firing. The heat requirement comes from the storage in the furnace, and it comes from the heat loss, including loss through the walls. So there are various types of heat losses. So next time we're going to talk about the heat storage and heat loss, but then we're going to get into the fun part of the course, at least it's fun for me, when we do some kiln simulation or optimization. So bear with me. In the next class, we're going to look at the last component of the kilns before we start actually pretending that we are firing something. So have a good time. Review this class as necessary. And I hope, even if you don't use solid fuels, you've learned a lot about particulate matter safety with combustible fuels and particulate matter safety from a personnel standpoint.